So yesterday's video, we talked about absolute value of x and about how the derivative did not exist at 0. So we're going to look a little bit more into that. Whenever we work with absolute value of x, we'll often redefine it. If f of x is absolute value of x, it's really just x when x is greater than 0, and negative x when x is less than 0. So for example, if we plug in positive numbers to absolute value of x, you get the same thing back. So that's why it's just x. When you plug in negative numbers to absolute value of x, you get the negation of that back. That's why it's negative x. So if we do our definition of a derivative from the right, that's the absolute value of x plus h minus absolute value of x all over h. Well, what that really is the limit as h approaches 0. Because we're coming from the right side, we're with our top part there, when absolute value of x is just x. That's the same as saying x plus h minus x over h, which is really the limit as h approaches 0 of h over h, which is just 1. So we looked at it just visually, but that's showing with our definition of a derivative that the derivative coming from the right is 1. We can do it similarly from the left. Absolute value of x plus h minus absolute value of x all over h. We'll now use our bottom function, where it's the negation. So really what we're doing here now, we've got minus x minus h minus the negative x. And that's because we're doing minus x, because we have x values that are less than 0. So this now is our limit as x approaches 0. This minus a minus becomes a plus, so we have negative h over h, so this is always just negative 1. Notice our limit from the right does not equal our limit from the left, therefore our overall limit at 0 does not exist, which is why there's no derivative at x equals 0. We just looked at it visually yesterday. Here's the mathematical reason why. So we mentioned in the video that what that is that's what we'll call a corner point. The corner point does not have the derivative existing because when your slopes from the left and the slopes from the right, they're staying at a constant value, and it's basically like they're jumping from one thing to another. We need them to eventually approach each other. So how can a function fail to be differentiable? One, we've talked about a corner point. That's the first one you see there. The next one would be what's called a kink. Think of like if you bend a hose, that forms a kink in the hose. That's probably where you've seen it in real life. But think about your slopes here. In the kink, when you're coming from the left, our slope is getting larger and larger and larger, but positive. Coming from the right, it's a larger and larger and larger negative slope. So our slopes are not approaching the same value, so that overall limit would not exist. That's why we would not have a derivative at that kink there. If it's not continuous at a, then it is also not differentiable at a. And if f has a vertical tangent line. So those are the three different places that we will see a function could not be differentiable. So here are two examples of places where there's vertical tangent lines. Because there's a vertical tangent line that has a slope that's undefined, so therefore we say that our derivative does not exist there. So again, our three things together: a corner or a kink on the left, a discontinuity Okay, it's not continuous at some value a, and then we've got our vertical tangent line. So we've talked about the first derivative and how we can represent it with f prime. We can do y prime. Well, we can also take second derivatives. A second derivative is just taking the derivative of the derivative. We will denote that often with f double prime x. And you see that here as well. And y double prime, those are the two most common notations that we will use for the second derivative. The other one that you might see is this here, saying the second derivative of y with respect to x. That's what that means. But again, these two are the most common ones you'll see. Y double prime, f double prime. So let's see if we can practice finding the second derivative using our definition of a derivative. We'll use a function we saw yesterday, x cubed minus x. So f prime of x we will find by doing our limit as h approaches 0 of x plus h cubed minus x plus h minus, the whole thing has to go in parentheses, x cubed minus x all over h. We've seen several times that when you have it cubed, it ends up as x cubed plus 3x squared h plus 3xh squared plus h cubed minus x minus h minus x cubed plus x all over h. We have a positive x cubed and a negative x cubed. They add to 0. Negative x, positive x, they add to 0. So we are left with the limit as h approaches 0 of 3x squared h plus 3xh squared plus h cubed minus h all over h. We'll divide out an h from everything. So we'll get 3x squared plus 3xh plus h squared minus 1. We'll now do direct substitution, getting 3x squared plus 3x times 0 plus 0 squared minus 1, giving us that f prime of x is just 3x squared minus 1. So that's our first derivative. To do our second derivative, we will just think of this as like our original function. So f double prime of x will be our limit as h approaches 0 of 3 times x plus h squared minus 1 minus, we've got multiple terms, so make sure you put it in parentheses, 3x squared minus 1 all over h. We've seen several times that this will FOIL out into x squared plus 2xh plus h squared minus 1 minus 3x squared plus 1 all over h. So this is 3x squared plus 6xh plus 3h squared. Maybe we'll just cancel out right now. Notice you got the minus 1 and plus 1. Might as well just get rid of those. All over h. Positive 3x squared, negative 3x squared. We've got the limit as h approaches 0 of 6xh plus 3h squared all over h. Notice everything in the numerator has an h. Divide it out. You got 3x plus 3h. Replace your h's. Oops, this should still have a limit. Replace your h's with 0. And we got the f double prime of x is equal to 6x. Now it asked up above, what is the meaning of the second derivative? Well, the first derivative, all of the y values represent the slopes of the original function. So the second derivative is really the slopes of the first derivative at any given x value. So if the first derivative has a slope of 1 at an x value, the second derivative will have a y value of 1 at that x value. So the second derivative's y values correspond to the slopes of the first derivative. Well, now let's see if we can keep going. Find the third and the fourth derivative. So we know the second derivative was 6x. Now as we keep going, it gets a little bit easier, it looks like. So f triple prime of x, our third derivative, would be the limit as h approaches 0 of 6 times x plus h minus 6x, only a single term, so we don't need parentheses, all over h. That would be the limit as h approaches 0 of 6x plus 6h minus 6x, all over h. That's the limit as h approaches 0 of 6h over h. Divide out your h. You've got the limit as h approaches 0 is 6. There's no h's to replace, so this is just 6 for f triple prime of x. And once you get past triple prime, they denote the next derivative of the fourth prime just by putting a little 4 in parentheses up there, saying it's the fourth derivative of x. And to be honest, we won't do too many derivatives that are past the third derivative, but for this case, they do want us to look at it. So we'll do the limit as h approaches 0. We've got to replace, remember, this is the function we're working with. We've got to replace our x's with x plus h. Well, there are no x's, so we'll just have 6 minus f of x is just 6 all over h. So we'll get the limit as h approaches 0 of 0 over h, which is just always 0. So our fourth derivative of x is just 0. Now let's think about these and see why these derivatives make sense. Our second derivative was 6x. That's a line with a slope of 6. No matter where we are on that line, the slope is always 6. Since your next derivative represents the slopes, it makes sense that our third derivative is always equal to 6. That's saying the previous derivative, the previous function, had always had a slope of 6. Well, now when we say the third derivative is 6, that's the function like y equals 6, which is a horizontal line. Horizontal lines always have a slope of 0. Therefore, when we took our derivative, that's why we got 0. It's saying everywhere in our third derivative, you'll just have a slope of 0. Now imagine if we kept going, the fifth derivative, sixth derivative, seventh derivative. Well, f of x equaling 0 is like saying y equals 0. Y equals 0 is still just a horizontal line. A horizontal line has a slope of 0, so if we just kept doing the derivative, we would just keep getting 0 back. Basically, we would have 0 minus 0 over h every single time when we did our definition of a derivative. So when it comes to physics, some of you that have taken physics have seen position, velocity, and acceleration. And we will work with that this year. Say s of t is our original function. That's our position function. Well, your slope in your position function can tell you your velocity. So that's why s prime of t represents the velocity of your object or your particle, whatever you're working with. Well, the slope of the velocity graph is telling you how the velocity is changing. So the change in the velocity, your next derivative, the second derivative, is your acceleration. We will work with those three a lot. S of t is your position. S prime of t, your first derivative, is your velocity. S double prime of t is your acceleration. Now the third derivative we won't see often, but that's what's called the jerk. That's the change in your acceleration. All right, let's see if we can find a couple more derivatives. To find our first derivative, f prime of, notice we're doing t here instead of x, we'll have the limit as h approaches 0 of 5 t plus h minus 9 t plus h squared minus just f of t, 5t minus 9t squared. Okay, again, we're just using t because they have t as the independent variable instead of x. So we'll have 5t plus 5h minus 9. We've seen several times that this will multiply out to t squared plus 2th plus h squared, and this will be minus 5t plus 9t squared when we distribute, all over h. We now have the limit as h approaches 0. And then we'll have 5t plus 5h. Distribute your negative 9 to give you 9t squared minus 18th minus 9h squared. And then the rest of the stuff. All over h. Positive 5t, negative 5t, add to 0. Negative 9t, positive 9t, add to 0. We're left with 5h minus 18th minus 9h squared all over h. We'll divide an h out of everything. That's 5 minus 18t minus 9h. Replace your h's with 0. The limit will go away. You have 5 minus 18t minus 9 times 0. And that means f prime of t is equal to 5 minus 18t. So there's our first derivative. Our second derivative, we'll do the limit as h approaches 0. 5 minus 18 times t plus h minus 2 terms, so we got to put it in parentheses. 5 minus 18t all over h. That'll be the limit as h approaches 0 of 5 minus 18t minus 18h minus 5 plus 18t all over h. We'll have a positive 5 and a negative 5, a negative 18t, a positive 18t, leaving us with negative 18h over h. Your limit as h approaches 0 after we divide out will just be negative 18. There is nowhere for us to sub in an h, so we just get that it's always, or sub in for h, we get that it's negative 18, and that is our second derivative. Now for our third derivative. We will have negative 18. There's nowhere to sub in an x plus h. Minus a negative 18 all over h, giving us 0 over h. So f triple prime of x is just equal to 0. And the fourth derivative would be the same. Now, something to note with these polynomial functions. We started with a quadratic. The first derivative was linear. The second derivative then was a constant. So notice our power, our largest power, our degree, goes down 1 each time when we are dealing with a polynomial function. That will come into play eventually. All right, we'll look at one more. We'll start out with the first derivative. We'll have x plus h cubed minus 3 times x plus h plus 5 minus, there's multiple terms, so put it in parentheses. X cubed minus 3x plus 5 all over h. We've seen a bunch of them cubed. Hopefully we are getting used to recognizing what it is. It'll make your life a lot easier. X cubed plus 3xh, or x squared h, plus 3xh squared plus h cubed. Distribute the negative 3. You get negative 3x minus 3h plus 5. Distribute your negative. You get negative x cubed plus 3x minus 5. And we are all over h. Positive x cubed, negative x cubed adds to 0. Negative 3x, positive 3x adds to 0. Positive 5, negative 5 adds to 0. So you got 3x squared h plus 3x h squared plus h cubed minus 3h all over h. Remember, everything in the numerator should have an h. Divide out that h. We get 3x squared plus 3xh plus h squared minus 3. We can now do direct substitution with this. When you do that, your limit goes away. We've got 3x squared plus 3x times 0 plus 0 squared minus 3, leaving us with the fact that the first derivative is just 3x squared minus 3. Notice we started with a cubic. Our first derivative is now a quadratic. We'll see if we can find our second derivative now. We'll have 3 times, first the limit. Three times x plus h squared minus 3 minus multiple terms, so put it in parentheses. 3x squared minus 3 all over h. We've seen a binomial squared several times. Hopefully by now you recognize it is x squared plus 2xh plus h squared minus 3x squared plus 3 all over h. Distributing that 3, we get 3x squared plus 6xh plus 3h squared minus 3. Actually, while we're doing this, let's save us a little bit of writing. The minus 3 and plus 3 add to 0, so we'll just have minus 3x squared all over h. Positive 3x squared, negative 3x squared. They add to 0. 6xh plus 3h squared all over h. Divide out your h. We get 6x plus 3h. We can now do direct substitution. When we do that, our limit goes away. And we get that our second derivative is just 6x. Our third derivative, this should be pretty quick. 6 times x plus h minus 6x all over h. Six x plus 6h minus 6x all over h. 6x and negative 6x add to 0. Our h's divide out, and we get the limit as h approaches 0 of 6. There's nowhere to sub in 0 for the h's, so we just get 6 for our third derivative. And if you thought that was fast, the fourth derivative will be even quicker. Nowhere to sub in, so we'll just have the limit as x approaches, or h approaches 0 of 6 minus 6 over h, which will just give us 0 for the fourth derivative. And again, that makes sense. Y equals 6 is a horizontal line. Horizontal lines always have a slope of 0. That's all for today's video. We'll see you next class, period.